Okay, I'll sign when I get back to my office.
So I have to forward it to the office after you sign.
I'll go ahead and do that. So once I sign, I'll forward it to the SME advising for you. Yeah.
Is there anything else I need to do after that?
So at the end of the semester, there's the bottom part of that form, and then yeah, I'll just sign at the end. Yeah.
Thank
Mhm. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Good.
Good to hear. All right, so it's Wednesday, week two. So it feels like the semester has started a lot, but then because of the holidays, it kind of still feels like we're still kind of getting going here. So, but today will be the kind of the first day where we kind of really get into actual content. So up until this point, we've mostly just been doing review of fluid mechanics. Um, all that's important, of course, but there's not much there that I can, for us to really do. So once we kind of get through this finite difference stuff and we start doing some problems, then hopefully things will, this class will kind of start to differentiate itself from it. Okay. All right. So I'm still working on your guys' first homeworks. The challenge so far is that we haven't really done anything where we haven't done anything where I can assign you guys problems to do because we've just been reviewing fluids. But I think after today, I think you guys will start to be able to start to do stuff with this finite difference stuff. So I'm hoping to assign the first homework by end of this week, and then probably give you guys about 2 weeks to do it. That's my plan for now. Okay. All right. Any questions I can answer before we get started for today? Yes.
Are the homeworks you're gonna assign from the textbook?
No, so I'll be writing the
You read them.
I'll be writing. Yeah. The textbook problems can be a little bit, so the thing with CFD is that it's hard to write good problems that are digestible, if that makes sense. So a lot of the problems you'll see in the textbook are either very theoretical in terms of like, here is this concept like proved, which are super interesting, but maybe not super useful. And then you have other problems that are like, do this very simple thing, which also is not that useful. And so I find it more useful just to kind of write my problems. Mhm. Any other questions? Okay. All right. So let's go ahead and get started. Okay. So last time we were here on Monday, we were kind of, talking about this idea of finite differences. So I'm just going to scroll up a little bit. So this should already kind of be in your notes. But basically the idea with finite differences is that, we are going to take our derivatives, our differential equations, and we want to replace them with algebraic expressions. Okay. And the way that we did that was we kind of built off this concept of, what does the derivative, visually represent for a function, right? So when we first learned about derivatives, right, derivatives is nothing more than just the slope of the curve, right? And one way that we can compute the slope is just to compute rise over run for the function. Okay. And so based on that concept, we came up with these three different expressions for the finite difference approximation of the first derivative, right? So we have our central differencing scheme, we have our forward differencing scheme, and our backward differencing scheme, okay? So basically they all represent the same derivative. It's just that they use different nodes or different stencils to get it done, okay? Now, kind of the thought that I kind of left you with on Monday is that, we have multiple finite difference representations of the first derivative. And that's also going to be true for the second derivative, third derivative, and so on. So, how do we actually go about choosing a scheme? Because, there's three options here. We only really need to use one, whenever we're doing calculations. So how do we actually choose which scheme to use? Okay. Okay. And that brought up this idea that, when you use finite differences, ultimately what you're doing is you're computing an approximation of the derivative. You're not computing an exact, emulation of that derivative. Okay. Okay. So let's write that down formally. So, when you make a finite difference approximation, that's only just an approximation of our underlying derivatives. Okay. Okay. And just like any approximation, there's always going to be errors or there's always going to be discrepancies involved when you're approximating something. Okay. So when I say approximation, approximation is nothing more than just you know, an imitation or an assumption that we're making. Okay. Um, there are ways where we can minimize the errors, and that's generally what we want to do, especially in a field like CFD where we want to minimize the errors. We want to minimize them enough such that they're not really noticeable, but there always will be errors, right? You're basically replacing one type of mathematical expression with a different one. Okay, so those two are never going to be the same exactly, but they can be close enough. Okay. And so the idea is that, when we're choosing finite difference schemes, we want to choose one that's going to have the smallest amount of errors. So how do we know which scheme has the smallest error? Well, um, for at least for the schemes that we've looked at so far, and with finite differences, there's a very elegant way that we can use to compute the error. And it uses something that, maybe you've probably seen in a previous math class many, many years ago that you probably thought you would never, ever need or use again. We're going to use a Taylor series expansion. Okay. So you can do a Taylor series expansion for any finite difference approximation. I'm only going to really go through the details for one, for just the forward difference scheme, just for the sake of time. But there are Taylor series expansions for all the different schemes that we'll use in the notes, and there's even more on the internet as well. Okay. Okay. So let's do, as an example, let's do a Taylor series expansion of the forward difference scheme, and let's see if we can use that to approximate the error in our approximation. Okay. Okay. All right. So if I know it's been a very long time since you probably looked at Taylor series, but the way it kind of goes is like this. And so, we have our function here, right? Let me go ahead and draw that again. Okay. So let's say that we have some point right here. Okay. Right. So this will be we'll say this is our xi. Okay. If we move to the right slightly, right? So let's say we move to the right by an amount delta x, right? This right here is going to be our function value we can call it phi at xi plus delta x. And so what the Taylor series expansion tells you is that, you can compute, or you can have an expansion of, the value of the function at that location shifted over based on the original. Okay. So basically, we're one way. So basically, the way we say is that we're going to expand the value of phi of xi plus delta x, centered around phi of xi. Okay. Okay. So let's see what that looks like. And so our series expansion looks like the following. So we have phi at xi plus delta x. Okay. So we're going to express the value of the function at our shifted location based on our original one. So this is going to be equal to phi at xi, okay, plus we have all of these derivative terms. And so, all the derivative terms that we're going to add account for the fact that, we're shifting our location a little bit. Okay. So for example, we have d phi dx multiplied by delta x. Okay. So that takes care of the variation that's due to the first derivative of phi as we move from one location to the other. Okay. So we take the derivative of d phi dx, or we take the derivative of phi multiplied by the grid spacing, delta x. We have a second order derivative term. We have d squared phi dx squared multiplied by delta x squared divided by 2. Okay. There is a third order term, d cubed phi dx cubed delta x cubed divided by 6, right? And technically it goes on. It's an infinite series. So, you can keep expanding more and more terms. Okay. But for our purposes, we only really need just the first couple terms. Okay. Okay. All right. So let's take this Taylor series and let's rearrange the terms a little bit. Okay. Okay. So let's do this. And so I'm going to take, first thing I'm going to do is I'm going to take this phi of xi and I'm going to subtract it from both sides of the equation. So I'm going to move it, basically, essentially move it over to the left-hand side. Okay. Right, so you have phi xi plus delta x minus phi at xi. Okay. That's equal to d phi dx delta x plus d squared phi dx squared delta x squared divided by 2 plus d cubed phi dx cubed delta x cubed divided by 6 plus dot dot dot. All right. Next thing I'm going to do, and so if you look at the left-hand side, you can see that that's almost what we have for our forward difference, right? So our forward difference scheme basically takes the difference between the function at the next location minus our current location divided by delta x. Okay, so we make that observation that this is almost forward difference. Okay. And so the only thing we have to do in order to get the forward difference scheme on that left-hand side is to divide by delta x. Okay. So I'm going to take this delta x, divide it by both sides, okay, and essentially kind of move it into that denominator there. Okay. Okay, and so if we do that, we get delta xi plus delta x minus phi at xi divided by delta x is equal to d phi dx plus d squared phi dx squared delta x divided by 2. Okay. Notice that when we divide by delta x, that's going to eliminate one of the delta x's on the second order derivative term. Okay. Plus d cubed phi dx cubed delta x squared divided by 2. Okay. All right, and then I'm going to stop here because that's this expression here actually has everything that we need. Oh, we need the dot dot dots. Sorry. A 6, yes, thank you. Yep. All right. So Taylor series representation probably was not on your bingo card for today, but this is it, I promise. And so I know it's kind of a lot to look at, but let's kind of break this down and see what information this kind of gives us. Okay. All right. So first thing we notice is that we've manipulated the left-hand side of this equation to give us our forward difference approximation. Okay. So everything on the left-hand side, this here is our forward difference approximation of the derivative. if you want to change the notation to be kind of more consistent with what we had last time, you can change phi at xi plus delta x. This is the same thing as phi at I plus 1. And phi at xi, this is at phi I. Okay. But it's just notation at that point. So. Okay. And then on the right-hand side, right? What do we have on the right-hand side? On the one hand, we have the first order derivative, right? So we have this is all equal to d phi dx. So this is exactly what we're trying to approximate. Okay. And so on the one hand, this Taylor series expansion gives us a little bit of reassurance that our forward difference, it has the thing that we're trying to approximate, right? But it includes a bunch of other stuff, right? And so everything on the right here, this is all of the other stuff, right? So everything I've circled in red there, those are the things that we don't want, because what those terms represent is those terms represent the errors or the approximation errors in doing our finite difference approximation. And in fact, those error terms have a very specific name in numerics. We call those the truncation errors. Okay. Because what we're essentially doing, and so when we do our finite differences, and we say that we're going to take our first order derivative and approximate it with the forward difference scheme, essentially what we're doing is we're taking everything that's circled in red and we're basically just getting rid of it, right? And so if we're just basically making this expression here, right? We're essentially truncating our Taylor series expansion and just accepting that everything that we ignored, that's going to be the error in our expression. Okay. Right. Hence the name truncation error. We're truncating that series expansion. Sure. Okay. All right. So through a Taylor series expansion, we can see that that's kind of what our error is represented as. Okay. Now you might be thinking, there are an infinite number of error terms there. So does that mean our error is infinite? Well, just because there are infinite number of terms doesn't mean that all those terms are significant. Okay, because I want to highlight something to you. Okay? And so if you notice, for every single one of our error terms, right, we have the derivative of the function, but we're also multiplying it by some term that involves the grid spacing delta x. Okay. Right, so all truncation terms. Right? And so in other words, you can say that our error terms are modulated by the grid space. Okay. Now, why is that significant? So normally when you're doing numerical calculations and you're creating a mesh for your problem, right? So whether it be a CFD mesh or a very simple mesh, like a square mesh, that what we're going to be using, to describe theory, usually you're going to choose the grid spacing to be fairly small, something that's much, much less than 1. And in fact, that's a concept that we'll go over, later on in the class when we talk about meshing, where, the finer your mesh or the smaller your elements or the smaller your grid spacing, the more accurate your solution is going to be. Okay. So this right here is, I would say, kind of the most pure representation that kind of shows why that's the case. Okay. Because as you make delta x smaller and smaller, then all of those error terms also get smaller and smaller, right? So there's a difference between using a grid spacing of 1 centimeter versus 1 millimeter, right? So 1 millimeter, those error terms are going to be much, much smaller magnitude. Okay. In fact, as delta x gets smaller and smaller, certain error terms are going to vanish faster and faster, right? So let's compare these two. So, I've kept these two here just so I can show you, right? So if we compare the error term, the first one here, okay? Well, yellow, okay? Right? So the first error term that we have here is modulated by delta x, right? Delta x to the first power. If we compare that to our second error term, well, I've kind of covered it with the circle there, but our second error term is dependent on delta x squared, right? As we make delta x smaller and smaller, which one is going to vanish faster? The squared, right? And so as delta x gets smaller and smaller, that term gets more and more insignificant. And then, you can kind of make that same assumption for all the error terms after that as well. So the next term that I didn't write is, d to the fourth, b dx to the fourth, multiplied by delta x cubed, right? And so that's going to vanish even faster, okay? And so actually, when you're talking about errors or truncation errors for finite difference schemes, most of the time you only really care about that first error term, okay? So this first error term, we often call the leading error term. Okay. Right. And in fact, the only thing we really care about the leading error term is its dependence on the grid space. Okay. All right. And so for the forward difference scheme, very basic forward difference scheme, we can see that the leading error term has delta x to the first power, right? And so the way that we usually say that is we say forward difference. Right? We say forward difference is a first order scheme. So you'll see this notation used sometimes. So you see big O in parentheses, delta x. And so that essentially means that our forward difference scheme is first order accurate. Okay. First order accuracy is not ideal usually. So usually, for a decent scheme that you're going to actually go through the trouble of writing a code for, you want at least second order accurate, but at least first order accurate will work. And so, you will get a vanishing error term because there are schemes where the leading error term is zero order accurate, and that is not a viable scheme. Okay, so at the very least, forward difference we can see is a viable scheme. The error term will vanish. It just vanishes kind of very slowly. Okay. All right. Any questions on this so far? Okay. All right. So that's the idea of truncation errors in finite differences. Okay. So forward difference, it's a good starting point, but it's we can't really use, or it's not favored because it's only first order. Okay. Now, I'm not going to go through the Taylor series expansions for the other finite difference approximations. They kind of just follow the same trend, and so it kind of gets repetitive. But I'll go ahead and list out the truncation errors for all the other schemes. Okay, so next we have backward difference. Backward difference is essentially kind of the twin sibling of forward difference. So backward difference is also only first order accurate. Okay. Which makes sense because backward difference is basically you're just looking to the left versus looking to the right. So it shouldn't really make that big difference. Okay. And then finally, we have the first scheme that we went over, which was central difference. So central difference is actually better. So central difference is actually second order accurate. And so actually, if you actually go through the Taylor series representation for central difference, you'll see that the leading error term it actually depends on delta x squared, and the delta x term kind of just goes away. Okay. And so based on this information here, we can see that we have a clear winner. Okay. And so in terms of accuracy between forward difference, backward difference, and central difference is the clear winner because it's the most accurate. All right. So second order accurate is a good threshold to have. There are more accurate schemes. And so actually, if you involve more nodes, you expand your stencil, you can actually get, third order accurate, fourth order accurate schemes for the first derivative. But usually when you get beyond second order, it kind of becomes overkill. And so my friend in grad school had a great saying that, he said that you could do more work to get more accurate, but oftentimes the juice is not worth the squeeze. Because if you're expanding your stencil, you're including more terms, that actually makes your programming a lot more complex. Okay. Central difference is actually very elegant because, in essence, we only involve two neighbor terms. We have involved the left neighbor and the right neighbor. So the fact that we get second order accuracy for such a simple scheme is actually very, very elegant. Okay. Okay. All right. So, for all intents and purposes, from this point moving on, we're going to be using central difference. But then you might be asking the question then, what's the point of forward difference and backward difference? Are they just always going to be the inferior siblings compared to central difference? Um, Turns out, those schemes do have a purpose. Okay. But we're not quite ready yet to kind of explain what their purpose is. But I don't want you to forget forward difference and backward difference. So it's like Neville Longbottom and Harry Potter. So don't forget about him. They're going to come back and save us. Later on in the class, maybe in about 2 or 3 weeks. Okay. Okay. So with that, let's also write out the finite difference approximation for the second order derivative. Okay. So I'm not going to derive this one. Just because just based on time, I'm just going to give it to you. Okay. So for a second order derivative, we have d squared phi dx squared. Okay. This is equal to phi I plus 1 minus 2 phi I plus phi I minus 1, all divided by delta x squared. All right, so I'm only going to give you one as well, because, actually for second order derivatives, we only really need one. Technically, there is a forward difference scheme and there is a backward difference scheme for a second order derivative, but those are almost never used. Okay. So this scheme right here, you can see it's, we're involving one right neighbor, one left neighbor. So this is a central differencing scheme. And as such, it has second order accuracy. Okay. So that's kind of perfect for our applications. Okay, good. So now we have our central differencing schemes for our first order derivative and second order derivative. You know, as I was reviewing kind of the notes that we went over last time, I didn't really say why we're doing this to begin with, right? And so I kind of said that this is kind of a build up towards finite volumes, but there's actually a very good reason why we're kind of going through this whole journey here, right? So why even bother, you know, with a finite differencing scheme and finite volumes is kind of the same way too, right? Why are we taking our derivatives and approximating them to begin? Okay. You know, because you know when you're doing a finite difference approximation, you know, we've already kind of conceded the fact that it is an approximation, right? So why would we bother, you know, taking a derivative and then representing it with an inferior version of itself, right? Well, the key is in kind of how this approximation is formed mathematically, right? And so if you look at our central differencing scheme for our second order derivative here, right? And you notice on the right-hand side that phi I plus 1 minus 2 phi I plus phi I minus 1, that right there is just a simple algebraic expression. And so the whole point of doing finite difference and finite volumes and finite elements is to take our derivative expressions, our calculus expressions, and essentially convert them into algebraic expressions. Okay. Now, what's so special about algebra, right? So the thing is, you know, a lot of these schemes, finite difference, finite volumes, finite elements, you know, they were designed to work with computers, right? And if there's one thing that computers are really, really, really good at, computers are really good at solving algebra problems. Okay? I guess more specifically, they're very good at linear algebra problems. Okay, even massive ones, right? And so, you know, when you think of, you know, when you ask kind of the average student, you know, what they think of, you know, when they think of linear algebra, right? You know, they tend to be thinking of, you know, maybe like, you know, three equations, three unknowns, you know, or if they're feeling, you know, kind of spicy, maybe five equations, five unknowns, right? Well, you know, when you're talking about, you know, CFD problems, computational heat transfer problems, finite element problems, you're talking systems of probably like 1 million equations and 1 million unknowns. And that even that is still pretty modest. And so, you know, I've seen, you know, codes that can get up to, you know, billions of equations and unknowns, right? So, you know, when I say algebra problems, you know, these are not the kinds that you can solve by hand. These are really massive problems that you can only solve with computers. Okay. But computers are really good at that, right? And so, you know, you can throw at them, you know, a massive algebra problem and they'll be able to find a solution pretty quickly a lot of the times. And there's even a lot of research right now to even make it even better. So, you know, I would say that like computer linear solvers are already pretty good, but there's a very, very active community. There's whole conferences built around this to say, like, how can we make it even faster? Because, you know, a lot of the computational algorithms that are very popular nowadays, and so not only on the physics-based stuff like CFD, finite elements, but, you know, a lot of AI is also driven by, you know, very powerful linear solvers. And so there's a lot of money to be had, you know, if you can come up with a better algorithm or better way for computers to solve linear algebra problems. So as long as there's still interest in that, if you can take your problem, whatever kind of complex physical problem that you have, and if you can turn it into an algebra problem, you can probably apply computers to it, and you can probably make a lot of money that way as well. Okay. So that's kind of the whole purpose of finite differences, is to, take essentially we're going to take our differential equations, our Navier-Stokes equations, and then convert them into an algebra problem for our computer to solve. Okay. So that's essentially where we're going to go. And that's what we're going to do next here, is that, we're going to take our complex governing differential equations, convert it to an algebra problem, and then, give it to a computer to solve. That's essentially our strategy with CFD. Okay. Any questions on this so far? Okay. All right. So with that, let's actually apply this to a problem, and let's actually start to do some actual problems, because we've mostly just been talking about theory this whole time. Okay. All right. So the next few weeks are going to follow kind of a pretty strict format, where we're going to take basically different parts, different components of our Navier-Stokes equations. We're going to apply finite difference to it, and then we're going to look and see how the solution forms. Okay. Okay, so we're going to start with the absolute simplest form of Navier-Stokes that we can think of, or that we can do, which is the 1D diffusion equation. Okay, so first thing I'm going to do, let me go ahead and start with our general transport equation, right? All right, so remember, we did this on Monday, where we took our Navier-Stokes equations, we applied various kind of assumptions to it, and we obtained this general transport equation. Okay. All right, so what it was we had, and I'm just going to do the 1D version. Okay, so I'm going to basically eliminate the 2D stuff. So you have u naught d phi dx is equal to g x plus nu d squared phi dx squared. Okay. Right. Well, remember, phi is our transport quantity here, where in this form, it represents some kind of quantity that can be transported with the fluid. So whether that be heat or mass, right? This is essentially just a heat transfer or mass transfer equation. Okay. Now, to actually start with the diffusion, we're going to make actually just one more simplification to make this as simple as humanly possible. And so we're actually going to eliminate the advective term. Okay. We'll bring it back later. Don't worry. It's coming back, but so we're kind of a long way away from Navier-Stokes now. So Navier-Stokes, in all of its glory, we've kind of taken away all of its stuff, and we're just left with the bare bones. Okay. And so all we're left with after this, and I'm going to take this g, I'm going to move it to the other side. And since that g is kind of unspecified at this point, I'm just going to make it a positive. I know you subtract it becomes a negative, but I'm just going to make it positive for now. Okay. So you have gx is equal to mu d squared phi dx squared. Okay. Right, and so all we're left with here is just a very simple, ordinary differential equation. Okay. And this differential equation here represents 1D diffusion. Okay. All right. So normally for an equation like this, it's a second order ordinary differential equation. Technically we can solve this analytically. So, we can use our techniques from, Math 250B or our EGME 308 to solve this. Okay. So technically, we don't need finite differences for this, but we are going to solve it with finite differences. And in fact, we're going to use the exact solutions to check and verify our finite difference solutions. Okay. Okay. So I think the best way, we spent so long talking about, finite differences and truncation errors. Let's just jump right into it. So let's just jump into an example. Let's solve. We're going to solve for the exact solution first, and then we're going to see how we can obtain that same solution using finite differences. Okay. All right. Finally, the first real example after 2 full days of just introductions and review. Okay. All right. So let's look at this differential equation. So you have d squared phi dx squared is going to be equal to 6x. Okay. So very simple differential equation. And let's say that we're going to subject this differential equation to the following boundary conditions. We're going to say that phi at 0 is going to be equal to 1. That'll be our constraint type boundary condition or Dirichlet boundary condition. And second one is going to be d phi dx at x is equal to 1 is going to be equal to 0. Okay. So our slope at the end of our domain at x equal to 1 is going to be 0. Okay. All right. And so based on this differential equation and based on these boundary conditions, let's solve for the expression for phi of x. Okay. Okay. So we're in luck here. And so, technically this is a differential equation, but since it's such a simple differential equation, we don't really need any kind of specialized techniques. And so we don't really need the characteristic equation, and we don't need to solve for the roots or anything like that. In this case, our derivative here is kind of just by itself. And so we can solve this, we can solve for the exact solution just using straight up integration. All right, so let's write it out. So we have d squared phi dx squared is equal to 6x. Okay. Let's go ahead and just apply an integral. So we're just going to integrate both sides with respect to x. Okay. All right, so it's a pretty straightforward derivative. So on the left-hand side, our integral is going to cancel out with one of the powers of the derivative. And so we're going to end up with a first-order derivative, okay, on the left-hand side. So left-hand side is going to be d phi dx. Okay. That's going to be equal to integral of 6x dx. And so we integrate that, we get 3x squared. And since we perform an indefinite integral here, there's no bounds on the integral. We have to add an arbitrary constant. So we're going to add a plus c, and we're going to need two of them. So I'm just going to add plus c. Okay. All right, pretty simple so far. So we're not quite there yet, though. So we need to integrate one more time in order to get phi of x on the left-hand side. So let's go ahead and do that. We're going to integrate one more time with respect to x. Okay. All right, so we integrate that left-hand side. We get phi of x. That's exactly what we want. And on the right-hand side, we have integral of 3x squared, which is just x cubed. Okay. Integral of c1. C1 is just a constant. And so that's going to be c1x. And then we need one more arbitrary constant because we're once again performing an indefinite integral. So we need our extra constant there, c2. Okay. So this right here is our general solution. We can obtain our exact solution or particular solution by applying our boundary conditions. So let's go ahead and do that. Okay. Okay. So let's apply our first boundary condition first. So our first boundary condition is phi at x is equal to 0 is equal to 1. Okay. So let's plug in x is equal to 0 in our general solution there. And what we get is 0 cubed plus c1 times 0 plus c2. Okay. All right, and so if we simplify this, we can see we get our solution for C2. So C2 here is going to be simply equal to 1. All right, so now let's apply our other boundary condition. So our other boundary condition is d phi dx at x is equal to 1 is equal to 0. Okay. So let's take our derivative and let's plug in x is equal to 1. So we have 3 x squared, so that's 3 times 1 squared plus c1. Okay. All that's equal to 0. And so once again, we can simply simplify this, and then we simply get C1. We move that 3 over to the other side of the equation. We get C1 is equal to -3. And so we plug those back in, we get b of x is equal to x cubed minus 3x plus 1. All right, and so that right there is our exact solution. So again, for this problem, it's just a simple second order differential equation. We can solve for the exact solution, but that's not the point of this class. So this point of this class is to solve it via finite differences. But we are going to use this because when we do get our finite difference solution, we need a way to basically verify if our solution is correct or not. Because this is our first time using finite differences. Well, it's not my first time; it's your guys' first time using finite differences. So. I want to show you guys that, what we're doing with finite differences, you do get a good result. And this is our way to basically check. Okay. All right. But that was kind of a very quick detour, 5 minutes of 308. Any questions on this? Okay. All right. So let's take the same problem and let's solve it with finite differences. All right. So let me go ahead and write out the equation again. So you have d squared phi dx squared is equal to 6x. Okay. Okay. So with finite differences, we're going to take our derivative here and we're going to replace it with a finite difference approximation. Okay. So we only have one derivative. It's just this guy. So let's go and do that. So for second order derivatives, the only finite difference scheme that we know is our central differencing scheme. So let's go ahead and do that. So we have phi I plus 1 minus 2 phi I plus phi I minus 1, all divided by delta x squared is equal to 6x. All right, good. All right, so we've taken our derivative and we've applied finite differences, right? Now where do we go from here? Well, when you're applying finite differences, you can't just replace the equation, right? You need to actually apply this to something, right? So one thing that we haven't really talked about yet is that, in order to actually solve a problem with finite differences, not only do you need to discretize the equation, you also need to discretize your domain, okay? So we need to basically take this and we need to apply it to a grid. Okay, so what does that mean? So from our problem, right? So let me just kind of scroll up here a little bit so we can see our boundary condition, right? So based on the boundary conditions that we're given here, we can see that our solution here is kind of defined between x is equal to 0 and x is equal to 1, right? Right? Because that's where our boundary conditions are defined. So, we can basically think of those as kind of the left bound and the right bound of our domain, or at least in terms of what we're interested in, right? So let's go ahead and draw that. Let's go ahead and draw that domain, right? So let's make basically a number line, and we'll have the left-hand side be x equal to 0 and the right-hand side be x equal to 1. All right. So we basically need to make a grid of points between these 2 points here, but that's what we're going to apply our finite differences to. Okay, so let's go ahead and define some discrete points between these two, right? So x equal to 0 and x equal to 1, those will be our endpoints, and then we'll kind of scatter other points kind of throughout the domain. Okay. So just so that we don't get too crazy, let's go ahead and define let's define 5 points. And so let me define one here, one at the halfway point, one right there. Okay. And we're going to go ahead and label all these nodes. So this will be node number 0, node number 1, node number 2, node number 3, and node 4. Okay. So 5 nodes total because we started counting at 0. All right, and if we do what we usually do here is we assume all the grid points are evenly spaced, right? We can write out the coordinates for each of these nodes too, right? So if the endpoints are x equal to 0, x equal to 1, we know node 1 here is going to be x is equal to 0.25. The location for node number 2 is going to be x is equal to 0.5. That's right halfway. And then node number 3 here is going to be 0.75. Okay. And so based on this, we can get an expression for the grid spacing. So our grid spacing in this case is going to be 0.25. So that means that the distance between each point is 0.25 meters, I guess you could say, although the exact units don't really matter too much in this case. Okay, so that's good. So that gives us at least something we can plug into our finite difference approximation. So if we plug in x equal to 0.25 here, right? And so we essentially have 0.25 squared, right? We can at least start to fill that in and get some numbers there. So I believe so. If we have 0.25 in the denominator, square, that's basically 1/16. And so that's going to multiply by 16 on top. But we can kind of fill in those details later. All right. Good. So what we hope to achieve here, so now that we have our grid and we have our finite difference approximation, right? Our goal is going to be to solve for the value of phi, or basically solve for the value of our solution at every discrete point in our grid. In other words, we want a value for phi 0, phi 1, phi 2, phi 3, phi 4. Okay. Right. And then based on those 4 points, that'll basically be our solution. Okay. Now this is quite different, right? And so if you compare this to the exact solution that we had up here, right? And so in the exact solution, we got a function of x, right? So we get phi of x is equal to some function that depends on x, okay? We're no longer obtaining that. So instead of a discrete function of x, or instead of a continuous function of x, we're solving for phi at these discrete points. So we have essentially a system with 5 algebraic unknowns. Right. So hopefully the problem is starting to kind of form in your head, right? And so if we have 5 unknowns to solve for, right, the way that we're going to solve for that is we need to derive 5 equations somehow. Okay. And so how are we going to obtain those 5 equations? Well, let's apply our finite difference scheme and let's apply it to every single node in our grid. All right. So that's our central strategy. Any questions on that before I start writing these equations? Because it's going to get a little bit repetitive at that point. Okay. All right. So let's go ahead and start. So let's go ahead and apply the finite difference scheme to each of those nodes. Okay. So we're basically going to be applying this equation here to each of our 5 nodes here. So I'm going to write out, basically each node here, right? So we're going to apply it to node 0, node 1, node 2, node 3, and node 4. Okay. And just to kind of make things just so I don't have to write the fraction here, I'm going to take, oops. Oh, okay. I'm going to take this delta x. I'm going to move it to the right-hand side here. Uh-oh. Well, hopefully you guys have the grid. Oh, okay. That was weird. Okay. I'm going to take this delta x. I'm going to move it to the right-hand side. Okay. All right. So let's apply this to node 0, right? So let me write out the finite difference scheme here just so it's easy to see. So we're going to have phi I plus 1 minus 2 phi I minus phi or plus phi I minus 1 is equal to 6x delta x squared. Okay. Where the I plus 1 refers to the right neighbor, I minus 1 refers to the left neighbor, and phi I refers to just the center node. Okay. So if we apply this scheme with node 0 as the center, right, we're going to get the following expressions. We're going to get phi 1 minus 2 phi 0 plus phi I minus 1 is equal to 6 x 0 delta x squared. Okay. Right. We can simplify this a little bit more because we know exactly what x0 is and we know what delta x is. Okay. And so if we do that, since x0 is equal to 0, this whole right-hand side here is going to be equal to 0, since x0 is equal to 0. All right. So let's do the same thing for node 1, 2, 3, and 4. So I'm just going to go fairly quickly here just because it's pretty repetitive. Okay. All right. So for node number 1, this can be phi 2 minus 2 phi 1 plus phi 0 is equal to 6x1 delta x squared. Okay. We know the value of x1, so x1 is just 0.25. And so this is 6 times 0.25 cubed. Okay. 2 ways to pull out my calculator now to find out what 0.25 cubed is, but Pretty easy to do. Okay. We apply the same thing to node number 2. We get phi3 minus 2 phi2 plus phi1 is equal to 6x2 delta x squared. This is 6 times 0.5, which is 3 times 0.25 squared. Okay. For node number 3, we have phi4 minus 2 phi3 plus phi2 equal to 6x3 delta x squared. X3 here is 0.75, so that is 4 times 0.25 squared. Okay. It was 4.5, excuse me. Okay. And then we apply this on the last node, we get phi 5 minus 2 phi4 plus phi3 equal to 6x4 delta x squared. X4 in this case is just equal to 1. So you have 6 times 0.25 squared. All right. A lot of writing, I know. That's why we asked the computer to do something. Question, yes.
Question for that cube on the first second node.
Yeah.
Where did that cube come from?
Yeah, it comes from the fact that x1 is equal to 0.25, right? So the location for node 1 is 0.25. Yeah. Mm-hmm. Yeah, good question. I kind of glossed over that. I did the math in my head and I put the cube there, but it's a good point to make. Question, yes.
Is there a reason in the row for 0 that you decided to leave it as the I minus 1?
Great question. We're going to address that in a second. Yeah. Oh, it should be phi not I minus 1, phi minus 1, excuse me. Yeah. But that is a good point to yeah. Mm-hmm. Any questions? Can we still write it down? Okay, good. So we have our 5 equations, right? And so, calculator notwithstanding, with computing 0.25 squared, we should be good, right? So these are 5 equations for 5 unknowns. Well, we kind of have a problem, right? And so if we look at all the middle equations, for node number 1, 2, and 3, those are actually all good. So those are good to go. But if we look at the first equation, okay, and if we look at the last equation, we have some issues with these, and we had kind of a preview of what that issue was, right? So the main issue is that, when you apply the finite difference scheme to those n nodes, you end up with some terms in your expression here that don't actually exist, right? Phi I minus 1 and phi 5, these ones do not exist because those go beyond our computational domain. Okay. And so we actually can't apply those equations to those nodes because we actually end up kind of stepping beyond our domain. Okay. All right, so we need to do something about the first and last equations, but everything else is actually okay. Okay. Because if we look at equation 1, 2, and 3, those all involve nodes or values of phi that that actually do exist, that are actually persistent. Okay. So what are we going to do with the first and last equation, right? So there's 2 pieces of information from our original problem that we haven't yet utilized in our finite difference approximation, and those are the boundary conditions. And so, you know, for 1D problems like this, for 1D problems, it's pretty straightforward because, you're going to apply the boundary conditions. It's always going to be the first equation. It's always going to be the last equation. For 2D problems, it's not as simple. And so you may have boundary conditions that are not there. But for now, you can basically assume that the first equation and last equation, you need to replace them with our boundary conditions. Okay. All right, so let me go ahead and write down our two boundary conditions once again, and then we'll do a little bit of kind of description in terms of what they represent and how we can actually incorporate that into our finite difference scheme. Okay, so our two boundary conditions in this example, we had phi of 0 is equal to 1, okay? And our second boundary condition is d phi dx at x is equal to 1 is equal to 0. Okay. All right, so let's start with the first equation because this one's actually the most straightforward, right? So what does this first boundary condition here represent, right? So if we wanted to describe this boundary condition in kind of plain speak, right? Basically what we're saying is that we are specifying or we're directly specifying the value of phi at this location. Okay? Right, so it's very direct in that sense. And so, we're not really going to go through any differential equation. We're not going through any, finite difference or anything like that. We're just saying that the value of phi at this location has to be 1, okay? So these types of boundary conditions where we directly specify the value, they have a special name. So these types of boundary conditions are called Dirichlet boundary conditions. Named after the, ancient mathematician that discovered this, right? So that's his name, Dirichlet. Okay. And so we need to be able to take this boundary condition and put it in a form where we can incorporate that into our system of algebraic equations. All right. So doing so is actually very interesting because, in one sense, the way that we incorporate that is very simple. But the way we actually get it to fit with the other equations is, maybe a little bit not so simple. Okay. So let's visualize this first. Okay. So I don't think we'll have time for the second one. So, we'll save that for Monday, but we'll do the Dirichlet boundary condition today. All right. All right. So this boundary condition, we'll say this is at x equal to 0 and say this is x equal to 1. Okay. This boundary condition is saying that at x equal to 0, then the value of phi must be 1, right? And so if we plot this out right here, right? We'll say this is the value of 1. That means our solution must start here. Or we can say the solution must pass through this point. Okay. Now let's go ahead and impose our grid, right? So we have node 2, 1, 3, okay. Node 0, 1, 2, 3, 4. Okay. So it turns out we have a grid point that coincides exactly with where the boundary condition is, right? So if we look at grid point 0 is exactly where we have this Dirichlet boundary condition defined. Okay. So what else is defined at grid point 0? Well, we have something that we're solving for there, which is phi 0, right? And so if we're directly if the Dirichlet boundary condition is directly specifying the value of phi at grid point 0, well, let's just write that as an equation, right? And so if the value of phi at grid point 0 is phi 0, then what we can say is that phi 0 must be equal to 1. So this is our Dirichlet boundary condition. Okay. So now let's take this equation and let's incorporate that back into our system of equations that we had before, right? So if you go back to our finite difference equations from our example, right? We had issues with the first equation and we had issues with the last equation. So let's take this equation here, this very simple phi 0 is equal to 1, and let's use that to replace the first equation in our finite difference system. Okay, so let's scroll back up here. All right, so we're going to eliminate this equation here just because it's, we don't have phi I minus 1, or we don't have phi minus 1. Okay. So that equation is not usable. And instead, what we're going to replace it with is phi 0 is equal to 1. Right? Very simple. Okay. And that equation there is perfectly viable, perfectly justified, because the only value of phi that's involved there is phi 0. That is a value of phi that we actually are solving for. That's actually part of a grid. And so that solves our problem on the first grid point. Okay. So when we come back on Monday, we'll talk about the Neumann boundary condition. And so, just as a preview, our Neumann boundary condition, we're going to use that to replace the last equation in our system. Okay. And then we'll finally be able to look at the solution to this problem. And so I'll show a MATLAB implementation. It's the MATLAB implementation. I've kind of been doing a lot of thinking about this class. And so, I'm not going to expect you guys to implement anything complex in MATLAB, but I will show you what the solution looks like just to kind of show you that it is legitimate. Okay. All right. So thank you guys for coming today. I hope you guys have a good weekend, and I will see you guys on Monday.
Can you go back to the chart thing?
Yes.
He's blowing it. Yeah.
Yeah.
Everybody.
Well, I mean, if you have to ask the instructor if they're okay with this. A lot of times it depends on if there's space in the classroom, right? You know, for me, I mean, that's why I kind of do too. And so sometimes the students have to be part of the course, and so I'm happy to really drop. Like it's only free ad. Yeah, yeah. You have to ask the instructor if they're okay. Thanks, guys. See you guys. What's that?
I kind of just had like a question about like this. I just like it's kind of hard to interpret it.
Yeah, I know.
Replacing like that first equation with like t zero zero one.
Yeah,
Like why it's kind of the same thing.
this is not the best stopping point. You know, I'm kind of doing things a little bit. I'm kind of jumping around a little bit just because of the first day was a holiday, but I promise you things will be more clear once we come back on Monday. But yeah,
Okay.
we stopped this equation we stopped this example at like kind of the worst time.
Okay.
Yeah, you don't see the full thing, you don't see the MATLAB, but yeah, it'll make sense on Monday for sure.
Are we gonna use MATLAB on Monday?
I'll show you the MATLAB, but
I see.
it's not something I'm gonna expect you guys to program,
Yeah,
but I just want to show it to you.
Okay, for sure.
Yeah, because I'm doing a lot more. I've been doing a lot of tutorials on OpenFOAM this week, and so I want to focus more on that. And so I think to get there, we're going to kind of speed through the MATLAB stuff. So I'll show it to you guys. I'll post the codes if you guys are interested, but it's not something I'm going to expect you guys to do.
Okay, for sure. Thank you. Appreciate it.
Yep.
Yeah, I wasn't injured in that, so that's all I can say. Great for that. So.